Hi, so I want to talk briefly about why the metamorphic facies boundaries might be fuzzy. Okay, so here's our metamorphic facies diagram, and we can see that these boundaries between eclogite, blue schist, green schist, amphibolite, and so on, they're not thin lines, right? There's not sharp boundaries that separate the green schist facies from the amphibolite facies. Now, Alan Glaser and I created this diagram with fuzzy boundaries for a reason. And the reason is that there really is variation between when one rock will shift from a green schist facies assemblage into an amphibolite facies assemblage. So if you look at just how fuzzy are these, you can see that we drew these with a bandwidth that's, not really 100 degrees, but something more than 50 degrees. So something on the order of 80 degrees. So we're going to call that plus or minus 40 degrees. Now, where did that number come from? Did we just make this up, or is there something more to it? Well, there's a couple things that can influence the range over which a rock can transform from one metamorphic facies to another. One of them is the composition of the fluid that is present. Now, most reactions that relate one mineral assemblage to another mineral assemblage in these sorts of rocks are related by dehydration reactions. So you might have a green schist facies assemblage that reacts at higher temperature to form an amphibolite facies assemblage plus water. Okay? Thing is, rocks are complicated, right? Not all fluids present in rocks are going to be pure water. They can have other stuff dissolved into them. For example, there's a lot of CO2 that can be evolved from other sorts of rocks, or there might be some carbonates in this system. And in that case, the water might not be pure. Instead of 100% water, maybe it's only 90% water. And maybe it's 10% CO2. Maybe there's other stuff dissolved in it and so on. Well, how big an effect is this? Well, we can look at this by looking at the displacement of reactions according to the activity of water. And I'm not going to go through a whole thermodynamic discussion of water activities, but let's just say that at this value, the activity of water is 1. And at an equivalent pressure and temperature condition, the activity of water in this kind of system, in a slightly diluted system, we're going to say is on the order of 0.9. So we want to see if I change the activity by 0.1, how much does it change the temperature? So here's an example of a dehydration reaction. Muscovite plus quartz goes to aluminosilicate K feldspar and water. And these are different positions of the reaction as a function of the activity of water. And so here's the pure water reaction. Here's 80% water, 70, 60, 50 activity of water. And we can see that if we pick some temperature that's kind of relevant to most metamorphic rocks, maybe not this low a pressure, but up here, we can see that it's about that far apart. That's maybe 20 degrees, okay? So that kind of effect will introduce an uncertainty in temperature of about plus or minus 10 degrees based on that particular reaction. We can look at other sorts of reactions. Here, for example, is a melting reaction, and this is the temperature where the activity of water is equal to 1. Here it is 0.9, 0.8, 0.7, and so on. We go up here, okay, here's at 8 kilobars, 0.8 GPa, and we look at that, and that's a variation of maybe 30 degrees. And so if we say, look, let's assume the system is mostly water saturated, maybe not completely water saturated, we can introduce an uncertainty in the position of the transition from one facies to another of something on the order of 10 to 15 degrees. So what other effects might there be? bulk composition of the rock makes a big, big difference. And so, yes, I know the metamorphic facies is defined according to the mineral assemblages that you would observe in a metamorphosed basalt, but basalts are not a constant composition, and what we call a basalt may actually be more towards the low silica side, maybe more like a basaltic andesite when we look at it in the field. There can be variations in aluminum content, calcium content, and so on. How much do those affect the position of a reaction? That's a much harder problem to solve, but fortunately, there are some experiments that have looked at some specific reactions. And so here I am looking at a tabulation. This is Green et al., 2016, Eleanor Green and co-authors. And they summarized a bunch of experimental data. That's what this little plot here is trying to show. And you can ignore the little blue bars. Those are theoretical predictions. Instead, what I want you to look at is take a look at these experiments, all conducted at 7 kilobars pressure, 0.7 GPa, in rocks that are broadly, well, these are actually andesitic. They're not quite basaltic, but these are fairly mafic andesites. And these bars are showing you the temperature at 7 kilobars at which the rock loses hornblende. Okay, so that's a dehydration reaction. That's one that's important for the transition from amphibolite facies to granulite facies. In fact, we even see the formation of orthopyroxene, a granulite facies mineral. And the point I'm trying to make here is that for this particular rock composition, the temperature of the reaction is around 975 degrees. If we look at this particular rock, the temperature is maybe 925 degrees. And if we look at this rock, the temperature is maybe 875 degrees. And so if we just look at these particular rocks, we can see a range in temperature at which hornblende is lost from the assemblage, and it ranges up to maybe even 100 degrees, certainly 50 degrees. And so in that context, bulk composition could have an effect on the position of a reaction, transition from amphibolite facies to granulite facies, plus or minus 25 to 50 degrees C. And then we can look at other systems too. We could, for example, take a look at this particular system. Now, this is in a metapolitic rock, a completely different bulk composition. But here we might consider, okay, so what is the difference in temperature if I have a rock where the garnet has an Fe over Fe plus Mg of 0.9 versus 0.8? Okay, let's just see what that kind of variation will introduce to a reaction boundary. So let's take 12 kilobars. We carry this down. That's a temperature of 540 degrees. And if we move it over by 0.1 and carry that down 540, that's going to be about 580 degrees. So 40 and 80, that's 40 divided by 2. So that's about plus or minus 20. Okay. Now, when we go back and we look at these boundaries and think about all the different things that might influence the position of that reaction, we can say, look, we don't know that the fluid is completely pure. We don't know exactly what the rock composition is going to be. One basalt is not quite the same as another basalt. And so we want to make those boundaries somewhat fuzzy. So where do we get plus or minus 40 degrees? Well, we know this has to contribute to it, so that's contributing a little bit. The kinds of numbers that we look at with respect to bulk composition are from 20 to 50. So we said, look, on average, these are probably going to be on the order of plus or minus 40 degrees.